Okay, I'm going to give two lecture right now. I'm sorry I cannot hear you guys, but I hope you can see what's going on and hear my voice. And if you have any question, please let the TA know so TA can communicate with me via either line or via the chat under the Zoom program. Okay, so the first lecture, I'm going to talk about Makefile. And there are actually two topics I'm going to talk about is separate compilation and as well as a Makefile. Let me see if I can play this. Okay, all right. So just let you know that what we have done. This is a review. So far, we've been talking about Unix and Linux tool and some of the basic operating system concept. Um, I try to finish this session uh, by the first lecture today. Okay, I do want to say that this is the review what we did the first week. I already showed the slide, talk about addressable memory box, what's memory address, as well as host by order, network by order, and those kind of concept. And the second weeks, we talk about what is operating system, which is essentially a piece of software that's between the hardware or devices and the application processes. And we also talk about what's the difference between a program and a process. The main difference is that a process is a activate program which has resources such as memory. And then we further talk about what we call under the virtual memory system, we talk about how the memory is allocated for every single process. And then you can actually see that how your memory, virtual memory, not physical memory, is being used. We also talk about what's the difference between potential difference between 32-bit architecture, which is a 32-bit address versus 64-bit address, because 32-bit address, the virtual memory for each of the process is 2 to the 30, 2 to the 32, which is gigabyte. And then we have 64-bit architecture, which is 2 to the 64. And that's 2 to the 64 is 64 etherbyte, which is a huge amount of memory, virtual memory space. So this is giving you some concept. And then what we did last week is looking at the how do you write a program to validate some of the concept. And particularly, we look at two programs. One is called stack01.c and the heap01.c. One of the things I do want to mention is that whatever we did last Thursday, that was something I consider fairly advanced for C programmer. So would be it's hard. It's not just because it's used a lot of pointer, but it's blending between the syntax of C and how you can use the syntax of C to validate some of the operating system concepts, such as memory layout. So it's difficult because it kind of blends so many concepts together. Uh, I know for most of you, probably this looks really hard, really challenging. I do want to encourage you is that I don't expect you to learn the whole thing the first time when you look over this topic. But I do want to encourage you to try to follow the program, at least stack01.c and heap01.c, so you kind of know how you might be able to expose the memory space that your program is dealing with. I mean, the important question I put in this slide is that the most important benefit for you to learn this concept is to really understand when or under what situation a specific region of memory will be overwritten or freed. So if you're using what we call local variable, which means that the variable will be placed on the stack. Whenever something on the stack, when the call is done, then the memory will be overwritten by another function call. That's why if you kind of follow stack 01.c, you kind of understand that what kind of situation your variable will be overwritten. That's one thing. But the heap 01.c, which is another memory area, is giving you the idea about when a piece of memory will be free. Because when you say delete, that piece of memory is gone. So in terms of stack.c and heap.c is corresponding to the question about when your memory, the data that you store in the memory, is still there, that you can continue to access the correct value. And under what situation those value probably is it means something else because the data has been either overwritten or has been free. So this is actually one of the very challenging issue for C or C++ programmer because in if you're doing programming in Java or programming in Python, you actually don't need to worry about this question. So under Java and the Python, there is a concept called garbage collection, meaning that the system will actually save the data for you automatically until they know for sure that this data is no longer needed. So this is the difference between C programmer and Java or Python programmer. Java Python programmer, they don't need to worry about the memory allocation. They don't need to worry about when will the memory be taken away for some other reason. But C and C++ program, you do need to worry about that. Therefore, it's technically easier to do the Java and Python programming from the memory management perspective. However, there is a price that we need to pay for using a system that support garbage collection. It's mostly related to performance. Okay, so that's what we did the second week. I will consider the second week is much harder than the first week. So if you have any question, please feel free to ask me. And this kind of concept, my experience, you won't learn the completely the first time, but you learn a little bit, and you do more programming, you do more exercise, then you will learn more. Okay, that's kind of the general spirit about learning programming in C or C++. Okay, I'm going to skip this part because I already talked about this. Okay, so I'm going to talk about the main topic I would like to cover today. It's called separate compilation and make files. I'm going to tell you the concept of how what do you mean by separate compilation, and then how this concept can go together with another Unix tool called Makefile, which help you to build the application. So first I want to provide some kind of difference. So now we're going to learn about GCC or G++. In fact, from this perspective, GCC and G++, they're almost identical in terms of their usage. So I first want to tell you there are three issues. One is called pre-processing. The second one is called compiling. And the third one is called linking. Okay, so this is for programming C or C++. You know that when you take in a program, which is a C or C++ program, you somehow make them into a executable file or executable program. So the when you write use the language called C or C++, when you first roll down the program, that program is not executable. You have to go through this preprocessing, compiling, linking phases, and then you can turn that generate into the executable program. So that's what we want to focus today. So first, I list about four different usage about GCC, and let's take a look at this. So I said the first usage of GCC, you put a minus capital E. I mean, let's just use an example. We're compiling this program we saw last Thursday called stack01.c. Okay, so if you do a compile, I mean, last week I told you we're doing the third option. We just take GCC stack underscore 01.c, which is basically generate the executable. So in other words, it's actually doing both all preprocessing, compiling, and the linking in one single command called gcc stack01.c. Well, however, the compiler G++ or GCC gave you different option that you can use this option to exercise one particular stage over the three stage. So usually is, for example, if you say GCC minus capital E, that means the compiler will stop after it's done with the pre-processing. So you might ask, what do you mean by pre-processing? Let's actually see, give you some example. Okay, let's actually come here. This is our this is our directory, and we have this program called stack01.c. Okay, so this is a program we did last time, and um, look at the first couple line, which is called include stdio.h and include stdlib.h. So you have some kind of header file. By the way, in C or C++, whenever we say header file, is usually is .h file, meaning that there is some kind of declaration about either function signature or some kind of data structure. You put it in those header file. So what preprocessor is doing, preprocessor is processing all the program that in your code that started with a pound sign. So whenever there's a pound sign, pound include, pound whatever, that preprocessor is trying to process this. So let's actually take a look at the program. I will use say GCC stack. Oh, sorry, I will say minus capital E because I want the compiler to stop at the preprocessor stage. And then I say stack 01.c. And then I will save the file. By the way, I do a greater than. This is called output redirection. I redirect the output to another file I call stack 01 dot capital E. Okay, so now let's take a look at the stack. Ah, now you see this is a program. Now it has a lot of this extra code. All right. So now starting from here is everything that's inside the stdio.h and uh, um, stdlib.h. So there is a lot of code being included from there. It's expanded. And one thing you will notice that there is no longer include in this file because include has been resolved with the file that's being included already. So let's actually get back here. Let's do a search main. Ah, here it here is the beginning of our program. If you remember, we have this foo, bar, and bus. And before bus was that include uh, um, uh, the two lines of include. So you can see that right now we're the whole program we're in 99%, and now we're in the line 1665, which means that those two lines, the expansion about those two lines, when you include the file, it has more than 16,000 lines of code being included. So this is called preprocessing. You kind of read those include line and then bring the code into this program before you move to compiling. So the first preprocessing, reads out all the include file, and then the second stage you will do compiling, and the third stage you are going to do linking, which I will explain to you. Okay, so this is so now next one I'm going to show you the compiling. Compiling, you have to do minus C. If you do minus C this way, that means it will do both preprocessing and the compiling, but not generate the executable file, which means linking. I will explain to you why it's called linking. Okay, so in this case, let me do this. Let me rm star.o. Okay, so I don't have. If you look at ls stack 01 star, you will see I have stack01.e, stack01.c. You don't need to worry about stack01.h. We'll talk about that later. Okay, so you have this file stack01.c, but you don't have the other program which I'm going to generate through the compiler stage. It's called stack01.o. So now let's do a compilation. Why is compilation? Because it's the minus C flag. Minus C flag means that it will try to take the source code and then generate the .o, which means the object file, which is the binary representation of the code. And then it will stop. It will not move on to do the linking phase, which is to link everything to produce a executable file. So after I done this compilation, if you do a ls minus l, you see that there's a new file generated. It's called stack01 .o, which is the just the object file. But let's actually take it to ls minus l. So take a look at the size of the whole program. First, you see that when you have the original program, which is the stack01.c, it has how many byte? Has about 1432 byte. That's basically the original code that we wrote. It's about 1400 character. But then when you do a capital E, which is you're generating the preprocessed version about the source code, include everything that's in the include file. Then suddenly this is actually make it a lot bigger, means 84,693 bytes. So it has this 1432, but it has a lot more that's being expanded over this include routine. Okay, So, and then we see that the .o file is about 2,300 bytes, which is the binary code that it has. Okay, let's actually get back here. So now I told you that if you do GCC minus capital E is preprocessing, it's actually resolve all the include. And then you do GCC minus C stack.c is doing compiling, is generating the .o file. But then the linking, you can do this. Let me actually now show you how to do this. Is that from that .o, I can generate executable. So let's actually come over here. I will do this. GCC stack 01.o, which is the object file I just generate. I'm going to generate output file, which is, I call it stack 01 dot, say, executable. Okay, so I generate this program. Now let's actually take a look. Now you see I have the stack 01 executable. So now I do want to say that stack 01.executable is also a binary file, but it's an executable binary file. But you look at stack 01.o is binary file, it's an object file, but it's not executable. So what's the difference between these two? You can see that stack 01 executable, when you want to make this file to be executable, the file become a lot bigger. Why is it a lot bigger? Because the linking program is linking not just stack 01.o, but also linking other file that might potentially be useful. Okay, so that's the kind of a few things that we went through. Is one is preprocessing, one is compiling, and one is linking. Okay, linking this file together. Okay, so I will give you just maybe 15 seconds for you to take a look, think about that, and if you have any question, please let the Richard know. So he will have a way to let me know regarding your question. Okay, any question? Okay, so I'm actually going to do my next one. So now I'm going to start talk about separate compilation. So what I just show you is that, okay, I have a stack uh, 01.c, and what I did was compiling is I generated this code called stack 01.o, and then I can generate a file. Either I call it a.l or I call it whatever I want with the minus o flag. So stack 01.c has been the example I gave last week, and also have been giving you what it does before this moment. Okay, so now I'm going to do something which is interesting. Okay, the way I'm going to do is this. I'm going to separate. I'm pretty much having a single program. Sorry, having exactly the same program called stack 01.c, but I separate this program into five different parts. So I still have the main program. I call it stack and stack 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 and also have another program called stack address.c. Okay, so let me first show you what this program looks like. By the way, all the code and all the PowerPoint file and a lot of other information has been uploaded to the GitHub directory. Okay, where's that GitHub directory? This one. Yeah, this one is the GitHub directory. I believe so. Yeah. Here you can see that I have upload a bunch of stuff with stack01.h, stack address.c, stack bar.c, stack buzz.c, and stack food.c. So let's take a look at the program, each of the program. Oh, I can just use this one to see it. Okay, the first one is stack main.c. So you can see I almost put every function by itself a file. Okay, so this file you see I only include file called stack01.h, and inside here I basically call a function called print return address 0 and function name, and then I call food. That's it. That's the program that in the main. I do want to go back to see the stack. Now I can show you what is stack01.h. So stack01.h is essentially both the include file and also a bunch of what we call function prototype. So function prototype essentially provide a signature about the function that you're going to use in one or more of your program. All right. So this is a stack01.h. It's just four function prototype, such as print return address, bus, bar, and foo. And this is important because when you try to compile, you can compile separately with such kind of definition file. Okay, so now let's take a look at the other three. Let's first look at foo. So stack foo.c is essentially only include that foo function, and then stack bar.c is the same. It only has that bar portion about the function within stack 01.c. And then finally, not the least, we have stack bars.c, which has a bunch of other things as well. Okay. Oh, this is bar. I clicked the wrong file. Bus should be this one. Yeah, this one is bus. It actually just I essentially chop the original program into a bunch of smaller programs, and all of them include stack01.h. Okay, so let's actually go back. And then finally, I have this program called stack address.c. Stack address.c is trying to dealing with the return address. I make it a bit more complicated because I want to kind of design a function I can use use the same function from all other files. For example, this I define a new routine called print return address. If you go to stack main.c, I actually call this function print return address. If you go to foo also use the function print return address. And similarly for the other program, which is a stack bar.c and stack bus.c, they both using the this particular function called return print return addresses. Okay, so essentially what I just showed you, I hope I convince you, is I take one program, I chop the program into four different parts. And why do I do this? So I can start to do the compiling. Let me actually show you how do I compile the program. One is the brute force way is this line. Too much. Yeah, you know what? I'm not going to do this. I'll just directly copy and paste. I need to go back one slide. I'm going to copy this line. If I copy all the file that I would like to do, and let me see the command, I'm going to do GCC like this. Okay. So essentially you see that because I separate the program into five different parts. So I one of the way to compile the program to generate executable is put all five of them together under the GCC command. So over here now I have this program just got generated is called a.out. Okay, so a.out is essentially the executable file that generate by this GCC whatever dot C file. Okay, so that's what we did. Okay, so that's one way for you to do the compilation. You kind of have a bunch of .o file or .c file. You just compile them together. Okay, so now I want you to think about this question because I'm not with you, so I probably cannot ask you the best way I can, but I still want you to think at the moment when you listen this. Is that I have a one approach. Approach number one is I have one single file include everything. That's essentially the first way. The second way is I chop the program into small uh, a bunch of small files, smaller files. And when I say those files, they either contain one function or maybe contain more than one function if I chose to do that. Okay, so my question to you is that why do I bother to do this, what we call separate compilation? Why do I bother to chop my own program into smaller granularity and let the compiler can actually link them together? Okay, so I want you to think because I cannot ask you a question right now. I cannot even hear you, but I want to just for you to have about 30 seconds to think about what's the advantage? Why do I even bother to do um, uh, this kind this kind of issue, which is having a bunch of smaller file and then just have compiler and linker works together to generate executable. Okay, think about this for 10, 15 seconds. Okay, I assume at this moment you have some idea about what do I mean by separate compilation. Okay, so now I'm going to introduce you another concept called the program is called make, but the data structure we store the most important configuration file to support the make is called make file. So I'm going to talk about what is a make and the make file at this moment. It's related to separate compilation, by the way. So what is a make? A make, as I mentioned earlier, is a software development tool. And while the make file is the one I can specify or I can configure the process, the software development process that's actually being supported by the make program. And then that's what I call a make file. And inside make file, you need to learn. The most important thing is called rules. So the thing is that if you look at the make file, it's essentially a bunch of rules, and those rules will be then triggered by the make program to do the job that you're hoping the make file configured to do. Okay, so if you never heard about make file, this will be interesting lecture for you. This, by the way, this is important because for the rest of the quarter, you will be using Makefile a lot. So it will be better for you to understand what is a Makefile at this moment. Okay, so let's think about this. Let's try to define what do you mean by a rule. So a rule has three components. One is called target, one is called dependency, one is called action. So the syntactically a rule looks like this. Means you have a target. After the colon, you provide a tab key, and then you have a bunch of dependent file that's going to supporting, which I will give you example. And then the second line, you're going to put the action. So the way to do it is that, okay, if I want to make a target, I need to first check my dependency need to be rebuilt. If all the dependency either have been rebuilt or they don't need to be rebuilt, if those conditions met, then you're going to execute the action. Okay, so let me give you an example about what's going on over here. So remember, we have this program called stack01.c, and we actually split them into five different programs, which is the stackman.c, stackfoo.c, stackbar.c, stackbus.c, and then stackaddress.c. So I kind of have a five file, but they all need to work together in order to support this final executable. I call it stack underscore executable. That's the file that we try to generate. Okay, so let me show you what is a rule looks like. That this is the rule I'm going to do. So what the rule is saying, the red part is called target, means that if I want to generate the executable file called stack executable, then it will depend on this 5.0 file. So essentially, this rule is saying that, okay, if you want to make a stack executable, you need to make sure that the five object file are already ready for me to do the action that's actually specified in blue color inside here. Okay, so in other words, if a rule basically say, hey, if you want to make a target, then I want to make sure that your dependency list being specified in the make file that has already been either has been built or you don't need to rebuild those files. I will give you a specific example about how that will work. But at this moment, I just want to let you know is that when I dealing with one particular rule in make file, that I need to first check the dependency list. If the check is done, then you will execute the blue part, which is the action part. And let's take a look at what this particular example, what is the action part, is GCC compiler. And then you can see I put 5.0 file here, five object file, assuming those five object file has been produced by probably another rule or is already exists over there. And then I linking all this 5.0 file together. And then I use -o option to indicate that, okay, the output file name, which is the executable file name, is called stack underscore executable. So that's just an example about a rule that how you can generate this stack executable output. Okay, so that's just one rule. So let's actually take a look at the real example. Take the whole make file which contain uh, more rules. Okay, so now let's get back to the GitHub. By the way, I already uploaded in the GitHub. So look for makefile. Okay, here is a makefile called makefile stack. Okay, makefile stack is the makefile we're going to do. Let's actually pick a makefile because I actually copy those two together. Okay, so let's take a look at this makefile. You can neglect this line number five and line number nine. It's just a macro definition. This capital CC is essentially, in this case, based on line number five. It's GCC. You're using GCC GNU CC compiler to do the rest of the rule. Okay, let's actually take a look at a few rules. The first rule, uh, all is the target. Okay, so I want to basically has a target. This target is called all. And then the dependency is stack underscore executable. And then there is a no action in this rule. So it's possible that you have a rule without any dependency or without any action being defined, and which is fine. But in order to make a rule, at least you need to have a target. Okay, so in this case, target is all, and then dependency is a stack executable, but then you don't have any action. Okay, so I will explain to you later that why you have this executable. Sorry, it's possible that you have a rule but without target. Okay, so let's actually now take a look at the rest of the makefile. I essentially has one, two, three, four, five, six, seven rules that being defined in this makefile. Okay, so before I tell you each of the file, let's actually try to run the experiment. I said make clean, and then I do make. You see that? It's been triggered a bunch of rule. It first trigger the GCC minus C minus G stack main.c, and then it trigger GCC minus C minus G stack underscore foo.c underscore bar.c underscore bus.c underscore address.c, and then you have the linking line, which is the last rule, which has GCC and all the .o file that's being this. If you take a look as one, two, three, four, five, there are five object file, and then you have a five line, which is each of them generate one of the .o file, and then the rule number six is basically put them together to actually get this executable called stack underscore executable. So you do dot slash stack executable, then that's the program. That's actually exactly like how you compile the stack 01 dot C and then generate the A.L. And this is our identical, except I'm using separate compilation. I'm using makefile to help me to generate the executable. Okay, so let's now go a little bit. We have a 3 minutes before we're done for the first lecture. So remember the first rule that is the all rule saying that depending on stack executable. So now you need to what this saying that okay, it will try to find if you have a rule, the target is stack underscore executable, and then it will try to execute that particular rule. So you see, I have a five or six rule, but the rule started at line 37 is actually stack executable. So by triggering that first rule, all rule, it will then trigger this rule on line 37, which is the stack executable. Okay. And then under the stack underscore executable, you have a five different. Can I move this a little bit more? Okay. Okay, fine. Can I make it bigger? Okay, fine, fine. That's fine. And it has a five different dependency: stack main.o, stack foo.o, stack bar.o, and start bar.o, and so on and so on. But the first dependency is a stack main.o. the same thing. We should look for a particular, whether there's a rule, the target is actually stack main.o. And then you realize, yes, the line 22 has a stack main.o, and then the dependency is stack main.c and stack 01.h. By the way, this says that this two, because I couldn't find rules that has a target of stack underscore main.c or stack 01.h. Therefore, I don't have anything more to do with the dependency. I'm actually going to execute this particular action, which is a GCC minus C stack main.c, which is exactly, let me do make clean, make, which is exactly this line. GCC minus C minus G, stack main.c. Okay. And then the second one is checking on the dependency list is stack foo.o, which is triggering another rule, which is starting with a line 25. And then it will compile the stack foo.c. And then it will compile stack bar.c. And then it will compile star bus.o. And then it will compile stack address.o. With all this file, then you can actually execute this particular line, which is essentially put this 5.0 together, 5.0 together, and generate the stack executable. Okay. Okay. I think my time is up for the first lecture. I'm going to stop here. We will take a 10 minutes break and then we'll come back to continue this topic. Okay.